Hello, my students. Hello, everyone. Hoping you're doing well, safe, and staying at home. Today, we're gonna discuss section 2 in chapter 18 about shifting equilibrium. The objectives is to discuss the factors that disturb the equilibrium, also the conditions under which reactions go to completion, and describing the common ion effect. Predicting the direction of shift. Changes in pressure or temperature or concentration. Keep these factors in mind. Pressure, concentration, or temperature can alter the equilibrium position and thereby change the relative amounts of reactants and products. According to Le Chatelier's principle, he stated that if a system at equilibrium is subjected to a stress, the equilibrium is shifted in the direction that tends to relieve the stress. Stress here means something change, something that got excess pressure or relieving pressure, increasing concentration or decreasing or something like that. This principle is true for all dynamic equilibria, chemical as well as physical. Changes in pressure, concentration, and temperature illustrate Le Chatelier's principle. To be more practical, predicting the direction of shift. Changes in pressure. A change in pressure affects only equilibrium systems in which gases are involved, due to the effect of gas pressure as we previously studied. For changes in pressure to affect the system, the total number of moles of gas on the left side of the equation must be different from the total number of moles on the right side of the equation. An increase in pressure is an applied stress. It causes increase in the concentration of all species. The system can reduce the total pressure by reducing the number of molecules, so that the reaction shifts in a direction towards relieving the stress of increasing concentration, leading to the direction of the lower concentration part of the chemical equation. The Haber process for the synthesis of ammonia, N2 gas plus 3H2 gas, nitrogen and hydrogen, producing ammonia gas, which is reversible reaction as shown. 4 molecules of gases are reacting. 1 mole of nitrogen reacting with 3 moles of hydrogen, therefore 1 molecule with 3 molecules, and so on, resulting 2 moles, and the molecules resulting also 2 molecules of gas. When pressure is applied, the equilibrium will shift to the right, to the number of lower concentration or the lower number of atoms or molecules to produce more NH3. By shifting to the right, the system can reduce the total number of molecules, which leads to decrease in pressure. Even though changes in pressure may shift the equilibrium position, they do not affect the value of equilibrium constant. Keep this in mind. The introduction of an inert gas such as helium into the reaction vessel increases the total pressure in the vessel, but it does not change the partial pressures of the reaction gases present in the reaction medium. Increasing pressure by adding a gas that is not a reactant or a product cannot affect the system, cannot affect the equilibrium position of the reaction system. Now let's move to the changes in the concentration. An increase in the concentration of a reactant is a stress on the equilibrium system. A plus B resulting C plus D. An increase in the concentration of A creates a stress according to Le Chatelier principle. How to relieve this stress? by shifting the reaction in the following direction to decrease the stress. To relieve the stress, some of the added A reacts with more amount of B to form products C and D. The equilibrium is re-established with a higher concentration of A than before the addition, and a lower concentration of B, of course. Changes in concentration have no effect on the value of the equilibrium constant. Such changes have an equal effect on the numerator and the denominator of the chemical equilibrium expression. The concentrations of pure solids and liquids do not change and are not written in the chemical equilibrium expression. When a solvent such as water in a system involving acids and bases is in an equilibrium equation, it is not also included in the chemical equilibrium expression. CaCO3, calcium carbonate, solid state, decomposes into calcium oxide solid and carbon dioxide gas. So the equilibrium constant is only the CO2, which is gas. High pressure favors here the reverse reaction. Here we have two molecules, one molecule and one molecule, resulting one molecule. And the low pressure favors the formation of carbon dioxide. Because both CaO and CaCO3 are solids, changing their amounts will not change the equilibrium concentration of CO2. But if we can imagine that this is a gas and this is a gas, also changing the pressure will change the direction of the chemical reaction according to Le Chatelier principle. Now let's move to another point, which is the changes in temperature. The reverse reactions are exothermic in one direction and endothermic in the other direction. We can conclude that heat or energy can be one of the reactants or one of the products. The effect of changing the temperature of an equilibrium mixture depends on which of the opposing reactions is endothermic and which is exothermic. The addition of energy in the form of heat shifts the equilibrium so that energy is absorbed. This favors the endothermic reaction. The removal of energy favors the exothermic reaction. Simply just like the concentration, increasing the concentration of one of the components or decreasing the concentration of the other one of the components. A rise in temperature increases the rate of any reaction. In an equilibrium system, the rates of the opposing reactions are raised unequally, and the value of equilibrium constant for a given system is affected by temperature. The synthesis of ammonia by the Haber process is exothermic, as shown to ammonia plus 92 kJ. At high temperature favors the decomposition of ammonia, the endothermic reaction. At low temperature, the forward reaction is too slow to be commercially useful. The temperature used represents a compromise between kinetic and equilibrium requirements. Here we can see the effect at the NO2 gas decomposes into N2O4 and vice versa. At 0 degree, the dominating here is the very light brown color. At 100 degree, the dominating is the dark brown color. While here in the room temperature, in the intermediate between 25 degrees Celsius, the medium brown. Changes in temperature also just give us a hint on catalyst. What is the catalyst? It is an element or a compound or anything that affects the rate of chemical reaction without itself being changed. Keep in mind that catalyst is not only used for rapiding the chemical reaction, it can also be used to reduce the speed or reduce the rate of the chemical reaction. We have positive catalysts and negative catalysts, accelerating and decelerating catalysts. So the catalyst is the compound or the element that enters the chemical reaction affecting its rate without itself being changed. Also, catalysts have no effect on relative equilibrium amounts. They only affect the rates at which equilibrium is reached. And catalysts increase the rate of forward and reverse reactions in a system by equal factors. Therefore, they do not affect K. That was all for today. Stay safe and check your LMS for your homework. Bye bye.